So, hey guys, before this podcast begins, there is a PowerPoint that could be really helpful for you, and it's linked in the description box below, so make sure you go check that out before watching, or actually listening to the podcast. Thank you. Hello world, we are SciencePod, providing you with the necessary knowledge and wisdom to succeed in the sciences.
Warning, this podcast may contain vulgar language and is not suitable for children, but for people who are wishing to get that A star.
We are not professionals, but we will try our best to teach our audience about the wonders of science.
This is dedicated to students by students. So sit back, relax, and we hope that you enjoy the podcast.
All right, exciting particle physics. Are you guys ready to learn?
Okay, so this is our second science podcast.
Wow. Okay, guys, whatever.
So today's episode, we're going to talk about particle physics, and we'll have some quantum and nuclear physics. I mean, the differences, I guess, between particle and nuclear physics is that particle physics looks at the most fundamental particles, whereas nuclear physics pretty much just looks at what's in the nucleus of an atom. So we're going to get that into a bit more detail than that. Okay, Ali, are you here?
Yes, I am here. I have returned.
All right, lovely. So we go to first slide. All right, first of all, let's talk about constituents of an atom with this lovely animation here. So this is pretty much GCSE, to be honest. So we know that there's a nucleus, yes? And Aaron, can you remind me what's in the nucleus?
Oh, is it protons and electrons?
Close.
Protons and neutrons.
Protons and neutrons.
I was nearly there.
Yes,
is
so the
electrons
things
the general
orbiting
name
them.
for it?
So the things orbiting them are what are called electrons. All right.
Yeah.
And the protons and neutrons are in the nucleus. I already said that, didn't I? Okay, lovely. So back in 1897, everyone thought the atom was the smallest particle of any element. And of course, different elements have different atom arrangements. So that's a bit of chemistry, really. So everyone thought, you can't get smaller than an atom, really. So they hadn't, at that point, discovered electrons or protons or anything.
Yeah.
Hydrogen, of course, was the smallest atom since it only had, we know now that it only has one proton. Okay. Yeah. So, Ali, tell us about J.J. Thomson.
Okay. So, basically, he's the one who discovered the electron. And now the atom is not the smallest particle, it's actually the electron. So, that's J.J. Thomson. I don't really know how he figured it out, though. Do you remember?
Fair enough. No, I don't either. Wait, no. Wait. What was the alpha scattering experiment? What was that discovering? What did that discover?
The nucleus? That all atoms...
it was a nucleus. Yeah, not the electron. Yeah. We never learned about how J.J. Thomson discovered. Yeah. Maybe we'll at uni. Well, I will.
Something to look forward to.
Yes, we can update the podcast when we know. Okay. So the electron, take it away, Ali.
So yeah, he discovered the electron, and you can see. Here's the thing. There is the same number of protons as there is electrons. Like, am I right?
Because yeah. In a stable ion.
An atom is always neutral. An ion. What's an ion, Sam?
It's a positively or negatively charged atom. So there's either going to be more electrons or less, basically.
Yeah.
How does one become positively or negatively charged?
To become positive, you remove an electron. So that's also called oxidation. And if you want to get negatively charged, you add an electron, and that's called reduction.
Okay. This is coming back to me now.
Yeah. We're still pretty much at GCSE level at the moment.
Yeah.
Thankfully.
So in the nitrogen atom, of course, I think the periodic in the table, it's in group 7, isn't it? No, it isn't. It's in group...
What? Which one?
Nitrogen.
Nitrogen is 6, so group 6. Because it has... Wait, is that...
It's
no, that's
7,
oxygen. It's group 4.
Group 4?
5?
It's 5. Okay, let's just forget this bit.
6 is oxygen.
Yes, 5 is nitrogen, isn't it?
Yeah.
7 is bromine, I think. Anyway. Okay. Next. Is my laptop working?
Yeah, there's 5 in the outer ring. How are we so stupid? Oh my god.
Oh yeah, we are stupid. Okay, right now it's working. Okay, so again, from GCSE, you know that the relative mass, so this isn't the actual mass of proton and neutron, it's relative. So relative to themselves, basically. So electron is very, very small. So I think it's 1 in 2,000. So very small, and relative charge again, +1 for proton, -1 for electron, 0 for neutron. Now the mass here, the mass here is displayed in kilograms. So kilograms is the SI unit. SI, what does that stand for?
Standard.
No, it's French for system international. Yeah.
So for mass, we always use kilograms. For charge, we always use coulombs. So there's SI units for pretty much every unit, and that's what physicists or scientists all around the world will use, really. Because if some Americans are using miles and Europeans using kilometers, it's not going to be helpful to work on the same thing together. Yeah. So as you can see, the masses of protons and neutrons here are very, very small. That's insanely small. We can't even comprehend how small it is. And an electron, again, is even 4 magnitudes smaller than that. Charge of a proton, so that's 1.6 times 10 to the minus 19 coulombs. And of course, since electron has the opposite charge but equal, it's negative. Yeah. So isotopes.
Okay. So it's basically a different form of the same atom. You want to think of it like, I guess, a sibling or whatever, you know? They're the same, but like different. And the thing that makes them different is the number of neutrons in their nucleus, okay? And like, an element has a specific proton number, and that determines the element. So yeah.
So you can have different neutron numbers, but the same proton number, you'd be the same element. Yeah. So you define an element with the proton number.
Yeah.
So.
Example.
God damn it! What's this slide? Honestly, it's not.
Sit down.
Oh, there we go.
All right, there we go. Yeah, so we just explained this. Okay, so hydrogen and carbon have quite a few isotopes as well. So we have deuterium, tritium for hydrogen, right? And we have carbon-12. Carbon-14 is quite a popular one. Carbon-14 is actually used to find out how old stuff is.
Yeah.
Yep.
It's used a lot in archaeology.
Yeah.
Biology.
Yeah. Oh, what does the 14 and like 12 mean?
Right. Okay. So in a carbon atom, as you can see, well, let's use an oxygen, right? So we have 8, and let's say that's 16. Okay. So that's the top number is the atomic number, aka proton number. So how many protons are there? And then we have the atomic mass, which is the protons and the neutrons added together, right? So 8 adds something is 16, and in this case, it's 8. So it has 8 neutrons in this atom. But if you see this number, it's not really 16; it's 15.999. So that's a bit weird. You can't have 15.999, protons or neutrons in an atom. So that's because there are a lot of different isotopes of oxygen. So to find basically the atomic mass, what we do is we find the average. So the average number of neutrons, in this case in an oxygen atom, is 8. And in this carbon atom, since it's 12.011, so pretty much 12. It would be 12 minus 6, so 6. Yeah.
So it's just an average.
Yeah, it's an average.
Of all the isotopes. Okay.
Yeah.
It's like the basics of stoichiometry.
Take it away, Sam.
Wait, what? No.
Come on. You take chemistry.
Go on, Sam.
Let's go.
You got this.
No.
I don't
So the atomic mass unit here is what we use to, well, I don't know what we use it. Well, we use it for some equation. I can't remember.
I remember learning it, but I don't know what for.
It's just a unit.
It is a unit. It's a 12th of the mass of the carbon atom. If you can see, it's very close to the mass of the proton or the neutron. And that's because it's that plus the electrons. And the electrons barely weigh anything compared to a proton.
So you want to say neutron? It's like a standardized unit, I guess?
Yeah.
Yes,
It's a standard, okay.
Oh, discovering radioactivity. Right, so Henry Becquerel, right? So anyone heard the units becquerels?
Yes.
Yeah.
Yeah? So Sam, what do you think becquerels are?
Oh no, go to Ali.
I don't remember.
I just heard of it.
It's a unit.
Yeah, it's a unit
of radioactivity?
Yes. Essentially, yeah. So becquerels are units for.
Oh wait.
Hang on. What's this?
I remember. Okay, so he's so that's Henry Becquerel. He's a French physicist. So in 1896, he discovered radioactivity because of photographic film and uranium and the emissions of so-called that. Yeah. Mm-hmm. I don't remember much, but that's what he did.
Anyway, so what Sam said earlier, so becquerel is pretty much the unit for radioactivity. And it's basically tells you the number of decays per second in the nucleus. So you might think, what does that even mean, right? Yeah. So hopefully the next few slides should explain that. So when atoms, right, they're not always very stable, okay? So especially uranium, you probably know that. It's quite popularly used in films and stuff. And of course it's used in like nuclear weapons as well. So atoms aren't very stable. So to become stable, they do some certain things. Undergo alpha decay, or they can undergo beta decay or gamma decay. So each different decay, something different happens. So in alpha decay, what happens is they lose an helium nucleus. Now, helium nucleus is 2 protons and 2 neutrons. So if you look at the atomic number, right, and the mass number, you can deduct 2 from the atomic and 4 from the mass. Oh, it's kind of awkward actually if you can't really see what's going on. But yeah, so you get a new element actually with alpha decay. And beta decay, instead of losing a helium nucleus, this time you lose an
electron.
It's an electron. Yeah.
Yeah.
And again, you get a new element, whereas in gamma decay, you don't really get a new element.
But anyways, what makes an atom unstable? Do they have like an extra shell? Like if they're losing one, I don't really remember.
If it has only like one electron in the outer shell, it's super unstable because it's easy to lose that electron. Yeah.
Okay. So and for it to gain, it's like just missing one in the outer shell. Okay.
That's why group 1 and group 7 are extremely reactive.
Okay. Do they only lose one? You can lose like 2.
You can lose, you can lose 4.
You can lose
but
4.
That requires a lot of energy.
Okay. Yeah.
So alpha decay and beta decay happens in like different kinds of elements. So alpha decay happens mainly in very, very big nuclei. So like uranium here has 235, protons and neutrons. And when you have so many, things in the nucleus, it's really hard for the strong nuclear force to keep them stable. Now, the strong nuclear force, we're going to get onto that pretty soon. But anyway, beta decay happens in nuclei with a lot of neutrons. So, what happens is a neutron in the nucleus becomes a proton.
Oh, okay. Okay, that makes sense.
Yeah, I remember.
Yeah.
Mm-hmm.
Properties of alpha, beta, and gamma.
Typical speed of alpha is a 10th speed of light. It has a charge of 2, mass 4, penetrating power is a few centimeters of air. Beta, almost the speed of light. Negative charge, 1 or 1,840 mass U, and it could only penetrate to 3 millimeters of aluminum. Gamma, it's exactly the speed of light. Charge 0, mass 0, and it could only penetrate through several centimeters of lead.
Basically, you can put them all on like a scale where alpha is like the slowest. It has the highest charge, it has the highest mass, and it has the lowest penetrating power.
And basically, gamma is the exact opposite, and the beta is in the middle for every single one. So it's quite nice. Yeah. Okay, so antiparticles. Aaron, are you still here, by the way?
I am here. I'm just nodding along. I don't want to keep interrupting.
No.
If you have questions, that's good. Please ask.
That's perfect.
Oh, okay. No. Okay, I will. I definitely will then.
Okay, right. If Aaron, all right, here's a good question for you. If I ask you the opposite of an electron, what would you tell me that is?
We didn't really learn that yet, but you can give.
Yeah, I know. It's just a random.
Give it a guess.
Give it a guess.
So I'm going to try and work this out based on the charge. An electron is plus. Is that right?
No, it's negative. It's negative.
Yeah.
It's a negative.
Yeah.
Okay.
So then we're going to need the one that's a plus. So neutron wouldn't be that. Is it a proton then? Is that right?
No.
You're close. You're close. You're very close. It's called a positron.
A positron. Yeah. Okay.
Yes. Okay. So
I'm just. You know what? I won't lie to you. Is that my knowledge is very weak from GCSE. So this is something I haven't. No.
You don't learn this on GCSE. That's why.
We don't.
Exactly. So
it's a trick question. You're not meant to get it right.
Well, I'm glad you asked it.
Yes. So it's a positron. So in GCSE, you learn only about 3 particles. About a proton, a neutron, and an electron. But there are more particles than that. So every particle has an antiparticle, right? So the proton has an antiproton, right? So a proton has a +1 charge. The antiproton has a -1 charge. Electron has a positron. A neutron has an antineutron.
What the hell?
Oh my gosh.
Right.
It's like the dark side.
Anti-neutral?
Anti-neutral, so the charge is still 0. And there's also something called a neutrino, but let's not worry too much about that. Again, that also has an anti-neutrino.
These all sound like superhero names.
Yeah, exactly. I was like, okay, there's the light side and then there's like the dark side that nobody really talks about.
Yeah, the Marvel heroes and the villains.
So can I just ask?
Yes.
Why is it if that they're similar properties? What does that mean? That they're the same, or like why do we not? Why do we not learn about this?
They just exist, but I guess nobody.
Oh, as in like, why do you not learn about it in GCSE?
Yeah, if it is important.
Oh, because it just gets a bit complicated, really. You learn about a lot of important stuff, but it gets quite complicated. So if you want to know, like, why do these antiparticles come from, right? And what happens when, like, I don't know, a particle and an antiparticle collide? So these are like different collisions or interactions, you can call them, right?
Yeah.
So have you heard of a photon?
Yep.
Yeah.
Remember in photosynthesis?
I won't lie. I'm going to say no. I'm going to do it.
Okay. What about you, Sam? Photon. Can you, any idea?
Yeah, photons of light, right?
Yes. Okay. Light is one. Yes, sure. Light. So photons really are just packets of energy of like electromagnetic radiation, and of course one of the electromagnetic radiation is visible light. So photons are quite commonly associated with just light, but really photons are pretty much radiation, or packets of radiation from electromagnetic spectrum. So it could have, so again, it could be radio waves, gamma ray. So a photon, what happens is the photon's energy is converted into a matter and antimatter. So it could be converted into an electron, which is matter, and antimatter, which is a positron, aka the antiparticle of an electron. So that's how antiparticles are created. And that's how normal particles are created as well.
Okay.
And so when a when a particle and an antiparticle, so again, we can use an electron and a positron, if they, bang together, if they collide, right? If they collide, as long as they have the minimum amount of energy, they produce two photons. So one going each way and the other way. It's all very geometrically. It's beautiful, right? It's just like, wow, everything's so perfect. But on a podcast, it's kind of hard to show that, I guess. Fundamental particles. Shall I carry on?
Yes, please.
Is this like quarks and stuff?
Yes.
Yes. Quarks. It sounds so cool, actually. Anyway, don't put that in. That sounds gay. Okay. Okay. All right. So fundamental particles. I'll leave you to this.
Okay. Yeah. For the past 120 years, many experiments have been performed to establish the nature of matter. So here's a timeline. So discovery of radioactivity, discovery of electron, and then you have the discovery of neutrons. Even at that time, other subatomic particles were being suggested. All the recent experiments have established that protons and neutrons are not fundamental particles. They contain quarks.
So before we even carry on, I think it's good to, let everyone know what a fundamental particle is. So this is essentially how small something can be, right? So again, back in the day in 1897, I think, or whatever it was, we thought atom was the smallest thing, there's nothing smaller. But of course, in GCSE, we learned that, no, you can get smaller than an atom. You can get to a proton, a neutron, an electron even, right? But in fact, now we found out that protons or neutrons, they're not just protons and neutrons. They're made of these little things, and they're called quarks, right?
I love that word.
Quarks.
They're so quirky. No, that sounds weird.
So quarks are in protons, neutrons, and of course antiprotons and antineutrons, right? Mm-hmm. And there's three types of quarks. Well, that we need to know for A level. It's up, down, and strange. And right? No. You think this is weird, but no. At uni, I think I'll learn about something called a charm quark.
Who named these? My God. Okay, correct me if I'm wrong, but it's like you can't actually see quarks, right? Because light rays can't be reflected off of them. Something like that. No.
You should do
Kurzgesagt video on it, and I was like,
Kurzgesagt is great.
Yeah.
So a proton, right? It has two up quarks and a down quark. A neutron has two down quarks and an up quark. Mm-hmm. So protons and neutrons are something called hadrons.
What does that mean, can I ask you?
So hadrons, right? It's just a lot of words. Okay. So hadrons are made of baryons and mesons. Okay. So baryons, right? Baryons are protons and neutrons. Okay. So they're the baryons that we know. And and then we have mesons, which are particles you probably would not have heard of. So there's pions, kaons. Yeah, so baryons have three quarks. So, for example, protons and neutrons, like you can see here, proton has up, up, down, 3. Neutron has up, down, down, 3. Meson, on the other hand, has a quark and an antiquark. Now, this must sound so confusing if you're just listening. You're just listening to up, up, down, quark, quark, quark. But really, honestly, when you see it on paper, it makes a lot more sense on how everything works. Okay, so classifying particles, we learned there are something called hadrons, and there are two types, baryons and mesons. So baryons are protons and neutrons, and mesons are like kaons and pions.
Are mesons? Oh, they only have 2 quarks, right? Or...
Yes, a quark and an antiquark.
Okay.
Yeah. Okay, and leptons are other fundamental particles. So, or for example,
it's just electrons, isn't it?
Electrons.
That's it.
Yeah. Muons are also leptons, and also neutrinos are leptons.
Okay.
Yeah. It's so confusing to listen to if you don't know what anything is. So strangeness. So we talked about up quark and down quark, but we never talked about strange quark, right? The reason is that they're quite strange, right?
Good one.
Yes. Honestly, I don't think we should go into this. It's really
it's just
hard
another.
to understand.
Yeah.
No, let's do it. I want to have an existential crisis.
Okay, all right. If we want to go into strangeness, we need to talk about the 4 fundamental forces. Okay, so there are 4 fundamental forces between any interaction in the universe, right? So 2 of them you're probably quite familiar with, right? So for the first one being gravity. Aaron, I don't know if you actually knew this. So gravity is actually acting on between every particle in the universe.
Every particle?
Yeah.
Every single particle. So even though Aaron is in London and you guys are on the Cayman Islands, you're still attracted to each other, right? I don't know if it's like that kind of attraction.
Dang. Oh my god. What about in space? There's no...
Yes, even in space.
Space,
even
really?
In space.
Wow.
Yeah. From one end of the universe, if there's an end to the universe, to the other end of the universe, everyone's attracted. Every particle is attracted to the other particle, right? So, yeah, you're attracted to the book as well, or like this laptop or your mic or whatever, and that mic is attracted to you, by different amounts. Like gravity on its own is like a really interesting topic to talk about, but the force is so weak. Like if you imagine, right, you're attracted to, again. So Aaron is attracted to Sam, right?
Oh, okay.
It sounds like a dating question. It's not. Okay. Okay, so Aaron is attracted to Sam, but I don't think that Aaron feels an urge to get closer to her.
That's not true. That's not true.
Like I'm pretty sure if they were in the same room, right? Let's forget they're in the Cayman Islands in London. Let's put them in the same room, right? If you told each other to stay still, they will stay still, right? They won't really get close together because the gravitational force between them is really, really, really weak, right?
Aww.
Because they're both of them, right? They're quite light, right? The reason you're attracted to the Earth, right? You're on the ground is because the Earth is really, really, really heavy. And the reason the Earth is attracted to the sun more than the moon is because the sun is really, 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 really heavy. That's basically why it orbits and everything happens, right? So that's gravitational force, and that happens between every single particle. Okay? Any questions on this?
So does that mean like gas planets they have like less of a I don't know what I'm trying to say.
As in because of the mass?
Yeah, like Saturn and stuff, because they're just gas planets.
Oh, so as in like we're assuming that because they're gas, they would be of lower mass than like.
Yeah.
Are
they not? Wait. Oh, mass.
I don't actually know.
Next. It's mass. Oh wait.
So the next force is the electromagnetic force. Again, this should be quite familiar. So this is what makes positive and positive charges repel, negative and negative charges repel, and like positive and negative charges attract, like like opposites attract and like charges repel. So electromagnetic force only acts between charged particles. So again, you would have seen this in like a magnet, for example. So if you put two of the same ends together, they would repel because there's an electromagnetic force acting between them.
Yep.
Yeah. Mm-hmm. So yeah, that should be pretty self-explanatory. You might see this symbol here that's called gamma, and that's because that's the exchange particle, a photon. So whenever there's an interaction, there's always an exchange particle or a gauge boson, I think that's called. And in this case, it's a photon. So for gravitational force, it would be a graviton. We all good?
No, that makes a lot of sense.
That makes sense? Yeah. Okay, if it makes sense for Aaron, it's good. All right. Okay, so weak force and strong force. So weak force, or the weak nuclear force. So the gauge bosons here are W plus and W minus. Again, don't worry too much about what they are. So again, they act between all particles, and who would have guessed the force is quite weak. And then finally, the most interesting one for particle physics anyway would be the strong nuclear force. So this strong nuclear force only affects hadrons. Now, if you remember what they are baryons and mesons. So they're the protons, the neutrons, the kaons, the pions. Only those particles are affected by the strong nuclear force.
Okay.
And this force is really important, right? Because if you think about it, in the nucleus, a lot of protons mice in together. And if they're all like charges, right? A proton is the same as a proton, like the positive charges. They should repel. So how are they able to stay in the nucleus? I'm sure Sam can understand that, because they're different, the same charges, they should repel, and they should really be as further away from each other.
Yep.
But the reason they're not is because of this strong nuclear force. So this force is very strong. So this force is so strong that it can basically counteract the electromagnetic force that's pushing it apart. So it can keep the protons together in the nucleus.
Oh, so how do the neutrons play the part of it? Does that help with the nuclear force in a way?
Sorry? So like...
Neutrons.
What part? So neutrons are also affected by this force.
Oh, okay. I heard that's what keeps them together.
Yes, yes.
Like glue.
That is, I can't really elaborate more on that, but that's as much as I know as well.
Okay.
So if you see this graph here, right, it tells you that between 0.5 and 3 femtometers, so that's femtometers, that's 10 to the minus 15 meters. So that's 15 zeros in front of, the distance. Only in that range is it's attractive, right? So it's a very short range force, this. And if you see below 0.5 femtometers, the force is actually repulsive. So if you think about it, otherwise, if you get two protons, it would just squish together so much, and that would be like a collision, right? We don't want that. We don't want them to collide, but we just want them to stay together, right?
Okay.
So can I ask you, sorry to interrupt, what regulates this nuclear force, or is that something we don't know?
What do you mean by what regulates? Like
what makes the nuclear force not too strong that it doesn't like smush them together in essence?
It's why? That's just the way it is, really. Why the force is that strong, but what affects really is the distance. So it knows that you can't get too much close together, because if you get below 0.5 femtometers, then it doesn't work, right? It's just repulsive. That's pretty much how the force behaves. And if it's too far away, again, like more than 3 femtometers, the force just won't work.
Yeah.
So the distance is pretty much what keeps everything together. So that's why as we get more, protons in the nucleus gets bigger. Because if you think about it, I mean, if you really tried, surely you can fit, 10 neutrons. I mean, 10 10 protons in the same nucleus as 8 neutrons if you really tried and squish them together. But this force, because of this, as you get more particles, then the room gets bigger, right? It's like how you can sleep. You can have 4 people sleep in the same room, right? But because of this force, it says only 2 people can sleep in the same room. And if you want 4 people, we need a bigger room. And the gauge boson for this are the pions. So the positive, negative, and pi zero. Anything else? Any questions? Sorry, that's what I meant.
Nope. I'm good.
No.
Okay. So Feynman diagram. So this can be used to represent interactions between particles. So like a proton and electron colliding, or a proton decaying, or a neutron decaying. And again, this diagram pretty much shows everything that goes in, comes out, and what's in the middle. You can treat it like an equation, like the photosynthesis equation we learned about 2 weeks ago. That's So this is pretty much a way of showing how interactions happen. Any other comments or questions?
Wait, do you want to go more into these diagrams?
If you can see the PowerPoint here. So what's happening here in the top left diagram is that there's a proton and an electron, and they are coming together. You see the P and then E minus, so they're the symbols. And what happens is a neutron is released and a neutrino is released. And to make this interaction happen, there's a W plus boson that pretty much is what makes the interactions happen, right? So this is when an electron and a proton collide. Bottom one's pretty much the same, pretty much really, just the boson's different. So the third one shows us the decay of a proton, because you see it's just a proton going in, right? There's nothing else coming in. So this is a proton, and what happens is it releases a neutron. So the proton turns into a neutron, right? And it releases a positron and a neutrino. So this would be beta plus decay, I believe. Yes. And the other one is a neutron decaying into a proton, and it releases an electron and an antineutrino, with the gauge boson being W minus. So that just sounds like I'm saying random letters and shit. But
yeah, so this is basically a detailed explanation of what happens during radioactive decay. Okay.
Yes, yeah. And these are just a few examples. There's like many more and they can get slightly more complicated, but if you just look at a few of them and you can see what's going on, they're not really that bad.
I guess you can kind of compare it to like an enzyme, sort of.
Like the gauge bosons, like the W's.
Yeah.
Is that what you're talking about?
Yeah.
Yeah.
But yeah, that's pretty much all my questions.
Are we done?
Yeah.
This is so interesting.
Question. Did you actually? I'm actually curious. Like, it's mostly from like Aaron, maybe Sam. Like, did you guys find that like understandable, interesting, or no? Like,
yeah,
honestly?
you're actually a really good teacher, because I have no science knowledge.
Okay, that sounds good. Thank you.
You know how much I hate physics, but like this was pretty interesting to me.
Okay, that's good. Hopefully, our views feel the same way. You know.
Yeah. Okay. Let's wrap up.
All right.
Make sure to follow us on our Instagram and YouTube at thesciencepod for more science episodes and updates.
If you like our podcast, please share it to your friends.
Be sure to check us out again before an exam. It'll be a huge lifesaver.
Thank you for tuning in, and see you in the next episode.